Inside your head right now, billions of brain cells are waiting for a signal. A biological neuron works like a bucket filling with water. It collects stimulation from the cells around it, and once it crosses a specific tipping point, a threshold, it suddenly fires a pulse of electricity. As we can see in this diagram of two connected cells, there is no such thing as a half fire. The sending cell either crosses the threshold and pushes an electrical signal across that gap to the receiving cell, or it does absolutely nothing. It is a strict yes or no decision. Back in the 1950s, an engineer named Frank Rosenblatt looked at this biological process and tried to build hardware that could mimic it. His early attempts required massive, tangled walls of physical wiring to recreate that simple yes or no decision. He called his invention the perceptron. You can think of it as a mechanical classifier, a machine designed to take a piece of information, weigh it against a threshold, and spit out a clean decision. To turn the messy biological spark of a human brain cell into a functioning piece of computer hardware, engineers needed to translate nature's tipping point into a rigid, reliable mathematical formula. Let's imagine a computer trying to learn the exact speed a rocket needs to travel to escape the moon's gravity. We can feed the computer a list of trial and error attempts. A speed of 1 kilometer per second results in a failure, which we'll call a 0. But 5 kilometers per second is a success, which we'll record as a 1. The computer's job is to find a mathematical function that evaluates any speed we give it and instantly returns a definitive 0 or 1. This graph illustrates how engineers originally solved this, the step function. The computer hunts for a threshold, marked by a sharp vertical wall, dividing failures from successes. If our speed is greater than this threshold wall, the computer confidently outputs a 1. But if every new task requires a different threshold, the computer's finish line is constantly moving. It's hard to build a standard learning system when you have to rebuild the basic rules of where the switch is located for every single task. Engineers needed a way to stop chasing moving targets. They needed to standardize the tipping point so it was exactly the same no matter what problem the computer was trying to solve. Instead of moving the threshold around, they removed it from the right side of the equation entirely and replaced it with a new adjustable number called a bias. By subtracting the bias, they effectively grabbed the entire graph and dragged it until that rigid step locked perfectly onto 0. Now it takes our speed, adds the bias, and asks one simple question: is the final number greater than 0? Anchoring the decision point exactly at 0 gives the computer a permanent, unchanging finish line. Calculating right and wrong answers suddenly requires a fraction of the processing power. But there is still one final roadblock. Look at the shape of that step. It is a sharp 90-degree corner, creating a vertical cliff. Computers learn through trial and error. If they guess wrong, they need to know how much to adjust their bias for the next try. A sharp cliff doesn't offer any clues about which direction to step. A computer needs a smooth, continuous slope to figure out how far off its guess really was. To create that slope, engineers swap out the rigid step for a smooth S-curve. This is what's known in computer science as an activation function. One common version is this S-shape, the logistic curve. The harsh vertical wall melts into a graceful slope. It still acts like our classifier. Top is a success, bottom is a failure. But crossing that mark happens gradually, showing the computer exactly how to adjust. By sliding down this smooth slope, the computer finally has the instructions it needs to adjust its bias, try again, and actually learn. Let's trace the journey of a single piece of information. We take a raw number, we add an adjustable bias so we cross 0, and we pass it through a smooth curve to get a clean yes or no. Our moon experiment used just one single input, velocity, but we can take this exact mathematical structure and stack it to evaluate dozens of inputs all at once. Imagine a computer reading a digital number. The digital display is made of 7 line segments that light up in different patterns. To classify a 1 versus a 7, the computer can't just look at one line. It has to read 7 different on and off inputs simultaneously, feeding each one into its own smooth, biased curve. It applies the exact same 0-point logic to all 7 inputs at the same time, combining the results to confidently categorize the shape it's looking at. When you stack millions of these simple decisions into deep layers, you get modern artificial intelligence. Every time your smartphone recognizes your face, it's using a massive network of these tipping points working together, all powered by Rosenblatt's original blueprint and the math trick of a biased tipping point.